Alright, so let me go ahead and go over these notes. First thing that I wanted to go over are radioactive isotopes. So we kind of touched on these when you were looking up elements. I made you look up the isotopes for each element. But now I'm going to kind of explain what they are. So if you have an isotope, it is going to be of an atom, so it'll be something on the periodic table. It's going to have the same number of protons and electrons, but it'll have a different number of neutrons. So basically, isotopes just have different masses. And they can be written one of two ways. You can have C14, where it's out here to the side, or you can have C14 and a 6, and so the 14 is on top, the 6 is on bottom. This number that's out to the side or on the top is a mass number. That's something that's new to us. It's not something we went over. So I'm going to explain mass number in a second. If it's written like this, it's got atomic number on the bottom. Alright, so mass number, most of the mass of the atom is in the nucleus. So that's the nucleus is like the most dense part of the atom. And what particles are in the nucleus? Okay, what particles float around on the outside? Yeah, electrons, like valence electrons are on the outside. So in the center of the nucleus is what? Protons and neutrons. Okay, so that's where most of the mass of the atom is. So therefore the mass number is the number of protons and neutrons combined.
Oh.
Okay, so that's what mass number is, just how many protons and neutrons you have total. To find the number of neutrons, you have to have an isotope to do that. So you may have something that's written out like this or like this one, and it may ask you how many protons, neutrons, and electrons it has. So if we're looking for protons, neutrons, and electrons, we can find protons and electrons by doing what? We're going to look at your... What number on here tells you how many protons and electrons it has?
The big number.
The whole number?
Yeah.
Okay, the whole number, and that's called the atomic number.
Yeah, that's
Okay.
what I was looking for.
Yeah, we're struggling today, but it's okay. We're getting there.
I'm still thinking about that Medicaid.
Yeah. Alright, so the atomic number will tell you how many protons and electrons it has. So let's look at the carbon-14. We know it's carbon. What's the atomic number of carbon?
I'm trying to find it 6.
Atomic number is 6. That means it has 6 protons and 6 electrons. So if we want to know how many neutrons this isotope, this carbon-14 isotope has, we're going to take the mass number, which is 14. That's the one that's given to you out to the side. Mass number either has to be given to you, because you're not going to know off the top of your head how many protons and neutrons it has. So it either has to be given to you, or they have to tell you how many protons and neutrons are in it. So it may say there's 10 protons and 8 neutrons. So what would the mass number be? 10 and 8 is 18.
Whoa.
Okay, so they either have to give it to you, or they have to give you how many particles, protons and neutrons there are. So to find the number of neutrons, we're going to take mass number and subtract away atomic number. So mass number, remember, is the number of protons and neutrons. Atomic number is the number of protons, and then we also know that's how many electrons it has since it's neutral. But it's a number. So basically, we're just subtracting off protons, and it's leaving us with neutrons. So 14 minus 6 is
8.
8.
I
So
can math.
then it's got 8 neutrons. So this isotope of carbon-14 has 6 protons, 6 electrons. We found that from the atomic number. The 8 neutrons, we took mass number and subtracted away atomic number and got 8. Alright, let's look at another one. This is another really common isotope. Carbon-14, have you heard that before? See, carbon-14? There is a C14, but have you heard carbon-14?
I've heard of C4.
Okay, it's not C4. Alright, so carbon-14 is what's used in radioactive carbon dating. You've heard that term before.
Yes.
So that, remember, like in 8th grade science, when we talked about radioactive dating, we talked about like absolute dating, where they try to get like a very, very close to the time, or they have relative dating, which just kind of gets you in a time period. So, like, you could look at a fossil and say, it's in this layer, so I know it had to be between this many million years and this many million years. Radioactive dating gets you closer to a time. So they could say, oh, well, this, by looking at how much carbon-14 is left in it, it should have been somewhere around, like, 5,000 years ago. And I'm fixing to show you how they kind of do that. So, carbon-14 is what they use in radioactive carbon dating, or if you just hear them shorten it down to carbon dating, that's what they're talking about. Alright, so we got uranium-238. So I want to know how many protons, neutrons, and electrons it has. So let's find uranium on your periodic table. It's down at the bottom in those two little things.
Can you give us a number?
992, I think.
92.
92.
Hey.
It's all the way at the
The
bottom.
cool thing with this one is it tells you how many atoms in the rings, you know?
Oh yeah, these army ones are pretty cool.
Yeah, because it's got like 2, 8, 18, wait, that's the wrong one. 2, 8, 18, 32, 21, 92.
Okay, so how many protons and electrons does uranium-238 have? What's its atomic number?
92.
So it's got 92 protons, 92 electrons. Now, for neutrons, we're going to subtract atomic number from mass number. So we're going to take 238 and subtract away 92. What's that going to be?
I got you. Alright, what is that?
238 minus 92.
92.
What?
92. 146, just kidding.
It's like, okay, so then it's got 146 neutrons.
That's pretty easy.
Yeah, so finding the number of particles is relatively easy. Just remember that with isotopes, you do have to either be given the mass number or you have to be able to add up protons and neutrons for it. Okay. Alright, does everybody understand how to do those?
Yes.
Okay. Alright, a couple other things. Nuclear terms. You've got alpha, beta, gamma. Alpha is your weakest nuclear particle. Beta is a stronger particle. And then gamma is the strongest. And it's a wave. So remember the electromagnetic spectrum I went over like the first day of summer school, I think? It was like radio, microwave, infrared, visible light, UV,
Solar flare.
X-rays, and gamma. Gamma was the strongest. Okay, so gamma is only produced in a nuclear reaction. So one odd thing about nuclear chemistry, everything we deal with in chemistry, physical science up to this point, the chemistry part, is always dealing with electrons. Bonding's dealing with electrons, talking about properties is dealing with electrons. Everything in chemistry has to deal with electrons until we get to nuclear chemistry. That's why it's called nuclear chemistry, because in the nuclear chemistry we're dealing with the nucleus. Okay, so nuclear reaction is dealing with the nucleus of an atom. That's why it releases so much energy, because you're actually either having to split it or you're having to fuse it. And when you split or fuse a nucleus, it releases a lot of energy. Okay, so everything we're talking about with nuclear chemistry is in terms of the nucleus. Alright, so alpha particles are the weakest particle. They can be blocked by like a sheet of paper. They don't have a lot of strength. If they're in alphabetical order, alpha, beta, gamma, they're in increase in strength. So alpha is the weakest, beta is the next strongest, gamma is definitely the strongest. Beta particles are a little bit stronger. That can penetrate through like some wood and stuff, but the most damage you're going to get with a nuclear reaction is going to be with the waves that are released from it, and those are gamma waves. So on your electromagnetic spectrum that's on your reference table, gamma is always going to be on the side that's the strongest side. They have a high frequency, short wavelength. Yeah, they bombard the area with a lot of waves in a small amount of time. That's why they're so dangerous. So, and I put the little symbols there. It's not necessary that you need to know those, but if you see that, that's what it is. When we get into chemistry, like if you take chemistry, we'll actually get into like what the particles are made up of, because it's just stuff that's split off a nucleus, so like protons and neutrons. And alpha has positive charge, that comes into play in chemistry, but for the most part, that's all you need to know. Gamma is the strongest, it's a wave. I did mention 2 words that you do need to know: fission and fusion. And you've heard these before. Anytime you hear about nuclear stuff, they're talking about fission or fusion. Fusion means it fuses. So what does that mean it does? If something fuses. Comes together, right? So fusion is where 2 atomic nuclei fuse into a larger nucleus. Alright, so fission is going to be the opposite of fusion. So what's it going to do? If these fuse, what's fission going to do?
Unfuse.
Okay, unfuse would be split. Okay, so this is where one large nucleus splits into smaller nuclei. Alright, so if we're drawing a picture of that fusion, if you see a diagram that shows that you've got like 2 nuclei, and it'll show like little arrows showing that they are coming together, and then you'll have a bigger one. That would be fusion. Fission would be where you have a big nucleus and then it splits off into smaller nuclei. A lot of times these show like little particles like protons and neutrons in it. And there's always something that triggers it, like it'll show a little particle that's triggering it in the diagram. Does anybody know how like they get a nuclear reactor to start? You know what they do? Process of it?
Water.
Water's to keep it cool because it releases so much energy that it gets so hot. If you don't cool it, what happens? What's that called?
Chernobyl.
Okay, what was that called? What's that called when it gets too hot?
A meltdown.
Yes, that's why it's called a nuclear meltdown. It is literally melting down everything around it because it gets so hot. But they actually drop a uranium, like a rod down, and the impact causes it to start the reaction. So it's always going to show this little thing starting the impact, like a little particle starting the impact, whenever you see a diagram of it. Alright, so I told you I was going to talk a little bit about, there's something over there I was going to relate to this. Oh, when I was talking about carbon-14, radioactive dating. So carbon-14 has a half-life of, I'm going to round it, it's like 5,700 years. Okay? So it takes it 5,700 years to break down like halfway. So, or to lose half of its strength. So if this was our original sample, then to break off into these 2 pieces, it took it 5,700 years. And then those 2 pieces are going to break down halfway, and that'll be another 5,700 years. And so on and so forth. Like every time it's breaking down, it's 5,700 years. So you can actually look at a sample and see like how long it's been breaking down based off of how much carbon-14 is left in it. And you can work stuff backwards too, like you can say we know we started out with this much, ended up with this much, like how many half-lives had to take place, so you can figure it backwards. We are not going to do any half-life figuring in physical science, but you do in chemistry. It's not hard at all, but it kind of looks confusing. So I kind of try to break it down in a diagram so you can understand what's going on with it. So it's just the time it takes for it to break down halfway. but that is like an exponential breakdown. It never stops. So it might be super, super weak, but there are still some of the particles there. So back to your uranium-238. Uranium-238 has a half-life of around, and once again I'm still rounded, but around 1 million years. So if uranium-238 leaks out, like at a nuclear plant, it's going to take it roughly 1 million years to lose half of its strength. So that's why radioactive particles are so dangerous, is because they do produce nuclear waste that has radioactive material in it, and it just doesn't go away. It's not something you can clean up or just make it go away. It has to run its course to lose its strength. So, nuclear energy is considered a green energy. Do you know why it's considered a green energy?
Because it's green.
No, not because it makes you glow green or puke up bile. If you get radiation sickness, you puke up bile, which is green, but no, not any of those.
It's from the earth. It doesn't cause pollution unless, like...
It doesn't cause what kind of pollution?
Air.
Air pollution. That's why they consider it a green energy. It's not really a clean energy because you have radioactive waste, but it's considered a green energy because it's not releasing carbon into the atmosphere. Okay, but it can contaminate the earth with radioactive waste. So, and a lot of the nuclear plants are not built really to code. They were kind of grandfathered in when they built them when there was this big nuclear like boom, during the Cold War, and we were setting up nuclear plants. And they weren't built really well. Chernobyl is a good example of it. It of course had a meltdown in, I think it was 86. I'm not 100% sure on that one, but it did have a meltdown. Still leaking radiation to this day.
Probably gonna explode again.
Like scientists say, the next Chernobyl, like quote unquote Chernobyl, will be Chernobyl because it's just going to keep getting like
Worse.
yeah.
Because there's basements that they can't get into.
They built a sarcophagus around the reactor that had all the problems, but they had to build it really fast, and that's collapsing, so it's still leaking out like crazy. And they can tell days that they have leaks because they still have sensors around there. There was a 200-mile exclusion zone, so from a 200-mile radius from Chernobyl had to be evacuated because of the nuclear radiation. So people have moved back into the exclusion zones. The government says it's safe now. It's not, but they say it's safe to live there. And some of your like weaker things like cesium, some of the cesiums and stuff, half-life of like 40 years. So it's lost half of its strength. It will in like a few years, but that's just the cesium one. It does get into food, so it is in their food. They do test food regularly over there. So fruits, vegetables, stuff that's grown in the area, it does have radiation in it. So it is a big deal if there is a meltdown. What was the most recent meltdown problem we've had with nuclear?
The one that was that damaging was Chernobyl.
Chernobyl.
There has been some scares like.
What was the one in Japan? Do you remember?
That was. It was near 2011, I think.
There was like it was a earthquake.
Earthquake and then it was
like
a tsunami.
Tsunami, and it was Fukushima power plant. So it's still leaking. I'm pretty sure too.
Yeah.
They can't contain it once it starts leaking. So it's fine as long as it's going good. But when you can't contain it anymore, then you've got a major problem. They are finding radiation in fish populations. So radioactive particles in like fish that they're like catching for food. They are finding like large bands of radiation in the ocean. I know y'all remember that deep ocean conveyor belt I told you about. It's like that. It brings the stuff up the upwelling, and then it rotates it around, and then it goes back down. And that can take like years and years. So we're not going to see. I mean, it can take like hundreds of years to go through that. Stuff can. So we're not going to see all the bad stuff coming out of it right away, just because it's so much, and it's in the water systems and in the like basically like the circulatory system of the earth right now. So, so nuclear is green, not clean. It's not, to me, it's not the best choice, but
It works